Hello, welcome to AB 313, Properties of Agricultural Biosystems Materials. This video we are going to talk about non-Newtonian time-dependent dilatant fluids.
What's our shear thickening materials, dilatants?
A dilatant, often referred to as a shear thickening material, portrays some extremely interesting material properties. Its viscosity actually increases with the applied rate of shear strain. Therefore, in simple terms, the harder and faster you push it, the more resistance you feel. This curious behavior means that dilatant materials and fluids are non-Newtonian. The following graph highlights this relationship. Shear thickening fluids, the apparent viscosity increases with increasing shear rate. The heart of the fluid is sheared, the more viscous it becomes. An example of this is mixture of cornstarch and water, which turns from being fluid-like to near solid when shear is applied. As you can see, it behaves very differently when the ball gently placed in the top of the mixture. It slowly but surely sinks. However, by applying more shear and an attempt to remove it, the solid-like qualities of the substance are demonstrated. We see that if the ball is dropped and impacts the mixture with a high initial velocity and greater shear force, its apparent viscosity is much higher. Shear thickening fluids, STFs, are examples of non-Newtonian fluids, a rare set of materials and fluids whose behavior deviates from Newton's law. Every action has an equal and opposite reaction. A dilatant material is a material that features an increase in viscosity and can even set to a solid as a result of deformation by expansion, pressure, or agitation. You might think that these types of materials are extremely rare and are only available for scientists to play with, but the truth is, dilatants can easily be created at home using simple ingredients such as corn flour, water, and even sand and water, etc. Child silly putty is also a great, everyday example of dilatant behavior.
What makes a fluid a dilatant?
Dilatant or shear thickening behavior is typically observed in fluids with a high concentration of small solid particulate is suspended within a liquid. Behaving like a true fluid under low shear stress conditions, dilatants then exhibit a transition to a more solid-like behavior when a greater shear stress or force is applied. The greater the force, shear, applied to a dilatant material, the more resistance you will feel. When subjected to extremely high levels of shear stress, dilatant materials can quickly become very rigid. Several factors control the behavior of the dilatant fluids, namely, the profile, particle size, spreading, and the proportion of particle density that are suspended in the fluid. The so-called suspension observes this behavior when it changes from a stable state to one of flocculation under the application of some type of stress. This happens because in cases where the material is subjected to high levels of stress, they quickly become very stiff. These are the example of dilatant foods. Peanut butter, it doesn't flow as easily as air or water, but will flow if sufficient force is applied, such as when a knife spreads it on bread. How easily it flows will also depend on temperature. You may have experienced peanut butter drips after slathering it on warm toast. Cornstarch and water. A good example of a dilatant fluid is a suspension of cornstarch in water. When a force is applied to a 1 minute and 1.25 seconds mixture of water and cornstarch, the mixture acts as a solid and resists the force. If such a suspension is compressed quickly by hand, the suspension will turn almost solid. If releasing the pressure, the suspension will flow freely again. Cream, it's also called a rheopectric fluid. Its viscosity increases with stress over time, so the longer you whip it, the thicker it becomes. Candy compound is also a good example of dilatant foods. Applications of dilatant traction control. Dilatant materials have certain industrial uses due to their shear thickening behavior. For example, some all-wheel drive systems use a viscous coupling unit full of dilatant fluid to provide power transfer between front and rear wheels. On high-traction road surfacing, the relative motion between primary and secondary drive wheels is the same, so the shear is low and little power is transferred. When the primary drive wheels start to slip, the shear increases, causing the fluid to thicken. As the fluid thickens, the torque transferred to the secondary drive wheels increases proportionally, until the maximum amount of power possible in the fully thickened state is transferred. Body armor. Various corporate and government entities are researching the application of shear thickening fluids for use as body armor. Such a system could allow the wearer flexibility for a normal range of movement, yet provide rigidity to resist piercing by bullets, stabbing knife blows, and similar attacks. The principle is similar to that of mail armor, though body armor using a dilatant would be much lighter. The dilatant fluid would disperse the force of a sudden blow over a wider area of the user's body, reducing the blunt force trauma. Theories behind shear thickening behavior. Dilatancy in a colloid, or its ability to order in the presence of shear forces, is dependent on the ratio of interparticle forces. As long as interparticle forces such as van der Waals forces dominate, the suspended particles remain in ordered layers. However, once shear forces dominate, particles enter a state of flocculation and are no longer held in suspension, they begin to behave like a solid. When the shear forces are removed, the particles spread apart and once again form a stable suspension. Shear thickening behavior is highly dependent upon the volume fraction of solid particulate suspended within the liquid. The higher the volume fraction, the less shear required to initiate the shear thickening behavior. The shear rate at which the fluid transitions from a Newtonian flow to a shear thickening behavior is known as the critical shear rate.